Okay, you can pause the video here if you prefer to read through my way of finding this limit through this yourself. Otherwise, I will go and erase everything here, and then you will see how I work from scratch to arrive at the limit of this. It's not very usual question for limit because it's quite difficult, right? Okay, so I'll just rub it off. Okay, it's one of the few concepts I've used in this is substitution, and then also using the Maclaurin's expansion approximation kind of stuff to get to the limit. So it is a bit challenging. You can skip this part of the video where I am erasing off all this, but let's see. Okay, if you get something like this, okay, so how do you actually do this kind of limit? What you will do is you do a substitution first. You let y equals to, anytime you see this type of where the variables and on top and below, instinctively you should think of, in the A-level syllabus, you should think of using the ln. And before you could use the ln, of course, you need to let this thing with a power equals to kind of a y or something. So if I let y equals to 2 to a power of 1 over n, okay, I'll just write it below. So if I let y equals to the power 1 over n, okay, then ln y equals to 1 over n ln 2, okay, and that means, okay, I got this substitution. I need to find out what is 1 over n, and 1 over n, I got it here. So that means my 1 over n is just equals to ln y over ln 2. So the entire this term, right, change to limit n approaches infinity. 1 over n is ln y over ln 2, and this 2 over 1 over n becomes y minus 1. But no longer makes sense to let n be the n approaches infinity because you don't see any n here. So instead, I change it to y. So as n approaches infinity, what happens to my y? My y approaches, because this approaches infinity, this term approaches 0. As this term approaches 0, 2 to the power of 0 approaches 1. Okay, so then we will have this equals to limit. Instead of, okay, writing it all over again, I just change this thing to, instead of n approaches infinity, I change it to y approaches 1. So this limit is the same as this limit. Okay, they are equivalent because it's derived from the substitution. So now that it is this case, so we still cannot, as y approaches 1, we still cannot know what is the limit because ln 1 is 0. Whenever you get 0 and bottom is also approaches 0, then you cannot make any sense of it because 0 over 0 is undefined, it's not a constant, so we can't make sense of it. So I need to do some changes to this again into something that is equivalent so that I can make sense of the limit. So what do? One of the things that I can think of is using, because ln y and y I will never be able to make sense, so one of the way I can think of is using Maclaurin's series to do an approximation. Since to do an approximation for this part. So since what do I do? So I do another substitution. Let z equals to y minus 1. Then my y will become equals to z plus 1. Correct? Then as y approaches 1, my z approaches what? So y goes to z, z goes to y minus 1, y goes to z plus 1. When y approaches 1, my z approaches 2. So is that alright? Not quite right. So let me get back to this part. Okay, so 2y minus 1 ln y goes to 1 and ln 2, 1 over n is ln y over ln 2. Okay, this part. So let z equals to y minus 1. So when y approaches 1, when y approaches 1, make a mistake. So when y approaches 1, z approaches 0. Okay, because 1 minus 1 is 0, so z approaches 0. Then it makes sense because for Maclaurin expansion, when z is small, I can ignore higher power of x. Why I'm talking about as Maclaurin expansion? Actually, I'm trying to do Maclaurin expansion for this term. So ln y actually becomes, since y equals z plus 1, so ln y becomes ln z plus 1. Okay, so z approaches because y approaches 1, z approaches 0. So we'll have this y minus 1 is z. Okay, so z ln 2. Z ln 2. Okay, so now we have something. Okay, so whenever we try to to differentiate between z and 2. Okay, so they'll make a mark here. So then then I do Maclaurin expansion for this part. I know that the z and z cancel away. In the end, it will give me 1 over ln 2. This is my intuition, but we need to prove it. Right. So because you can use the standard series, if you're talking about the A level, you have the MF15 formula sheet. You can use the standard series expansion for this. If not, you do Maclaurin series expansion. For Maclaurin series expansion, the formula is this. So f0 plus f prime 0 over 1 factorial x plus f double prime 0 over 2 factorial x square, so on and so forth. But we know that since z is 0, is very small. So if a very small term, if you square it, is insignificant. It's not significant, so you can just ignore this term. But it is significant up to z because there's a z at the bottom, right? You still need to cancel it away. So then we have, in this case, this is the general Maclaurin's expansion, but in this case, our fz is equals to ln z plus 1. So what is that means our f0 is just equals to ln 1, which is equals to 0. Now, if we did not do this, we cannot do Maclaurin expansion for ln y because if fx equals to if fy equals to ln y, then f prime y equals to 1 over y, and we substitute f prime 0 equals to, it will goes to undefined. It will be undefined. So we cannot do for ln y. So that's why the substitution y equals to z plus 1. Okay, and that is okay. So then we do f prime z, that means differentiating this one time. So this one, when f prime z means differentiating this inside first, I'll get 1 over the inside. Okay, this is the formula for differentiating a ln function. Okay, that means okay, since we have this, then f prime 0 equals to 1 over 0 plus 1, so it's just 1. So then we have the Maclaurin expansion ln fz equals to, so ln z plus 1 approximately equals to f0, which is 0, plus 1 over 1 factorial times the x. Okay, I can go on, but it doesn't make any meaning because x squared is even smaller than x, and when z approach this should be a z, sorry, because we are expansion is in terms of z. Okay, so then we will have when z approaches 0, this is already very small. Even if you have a z square, z square will be even smaller than this term, so it will be so insignificant that we can exclude it. So then we have the expansion, so ln z plus 1 is approximately equals to z when z is small. So I have z limit z approaches 0, z over z ln 2. So when this cancel out, I'll have 1. So limit z approaches 0, I don't have anything to substitute in, so it's just 1 over ln 2. This is my limit for this. So you realize yeah, okay, and that's it.